Hi, Assalamualaikum. We are from Group 6. Today we are going to present about our project, which is the process of crystallization in unit process. The overview of the presentation is shown in the next slide. So this is our team members, which are me, Nonisa Izzati, Norhani Umairah, Lutfi Adil, and also Moza Zetino.
So for abstract, this study aims to publish innovative theoretical and practical methods for modeling and controlling crystallization processes in development and also commercial manufacturing.
By using Microsoft Excel, measurements and calculations were performed to assess mass flow rates and energy consumption for heating, cooling, and also phase change. The findings provide insights into the efficiency of the crystallization process. It also suggests improvements for energy conservation and process optimization to improve final products' quality and efficiency.
So for the introduction, the crystallization is crucial in chemical engineering and material science for isolating, purifying, and synthesizing substance. It involves nucleation, crystal growth, agglomerations, and breakage to produce high-quality crystal efficiently. This process is vital in industry like chemical, food, and pharmaceutical, with solution crystallization being favored for its efficiency and low pollution. Recent advancements include using ultrasound, wet grinding, and spherical crystallization for better nucleations and particle formations. Continuous crystallization is preferred for its productivity and consistent quality. Effective design and control are essential due to the process complexity, with the modern tool like a process analytical technology and simulation aiding in development. Understanding crystallization kinetic through experiment is critical for designing effective crystallizer with a technique like a cooling batch with setting improving outcomes.
Freedom. So based on the given process diagram, calculate the mass flow rates of a water vapor, which is M2, and the potassium chloride solution, which is M5. Given the mass balance around the evaporator where the fresh feed is equal to 96 kg per hour combined with the recycled stream, which is MR 69.1 kg per hour, to produce an output stream, which is M1 equal to 165.1 kg per hour, and water vapor M2. We determine the M2 using the equation of M feed plus MR equal to M1 plus M2. Additionally, for the crystallizer and filter, with the output from the evaporator, which is M3, equal to 86.3 kg per hour, splits into potassium crystal, which is M4, equal to 14.6 kg per hour, and potassium chloride, which is M5. So we can calculate M5 using the equation of M3 equal to M4 plus M5.
So, the formula used to perform degree of freedom in the system is the number of unknown minus the number of independent balance and the number of other equations. It helps to determine whether a process is fully defined, over-specified, or under-specified. The number of unknowns refers to the variables in the system that need to be determined, for instance, the flow rate and concentrations. The number of independent balance, it represents the independent mass and energy balance equations that can be applied to the system. For the number of other equations, it includes any additional relationship, such as equilibrium equations.
So let's begin with the overall system. First, note down the total inputs and output and set up the equation MF plus MR equal to M1 plus M2, where two unknown, which is M2 and M5, and two knowns result in a DOF of 0. Next, move on to the evaporator and set up its mass balance with equation M1 equal to M2 plus M3. It introduced three unknowns, which is M2, XK1, and also XW1, and two unknowns leading to a DOF of 1, indicating the need for an additional specification to fully determine the system. For the crystallizer, the equation is M3 equal to M4 plus M5, introduce the unknown XK4, XW4, and also M5, and two unknowns plus an additional known from the aqueous solution, yielding a DOF of 0. And finally, in the mixer, the equation is MF plus MR equal to M1, with two unknowns and two knowns also results in a DOF of 0.
So, lastly, this calculation that for the overall system, the crystallizer and the mixer, and the number of the equation match to the number of the unknowns, resulting in a fully determined system with a degree of freedom of 0. However, the evaporator has a degree, 1 degree of freedom, meaning that the one electrolyte specification is needed to fully determine the system. So we move on to the mass balance.
For calculation of mass balance, this process of crystallization was carried out in multiple unit operations. Thus, the rules behind this material balance are what goes in must come out. That means that the total mass into and out of a unit should always be equal to achieve the maximum efficiency and avoid releasing hazardous chemicals. The crystal produced in M4 are recycled back by filtering it, then it is allowed to the mixture to react again.
So fresh feeds enter the system at a flow rate of 69 kg per hour, consisting of 60% of potassium chloride and 84% of water. But this feed is mixed with the recycled stream in the mixer, resulting in output flow of 165.1 kg per hour, but the composition of this stage is unspecified. So the composition of the output stream was calculated by using components balance of K and W for the mixer. So the calculation was followed by the formula of ZK times MF plus XKR times MR equal to XK1 times M1 to calculate the composition of XK1, which is the value is 0.213, while the formula of ZW times MF plus ZWR times MR equal to XW1 times M1 to calculate the composition of XW1, which is the value is 0.781.
The mixture then moves to the evaporator, which removes an unknown amount of the water vapor. The water vapor M2 was calculated by calculating the overall materials balance OMB of the mixture by using the formula of M1 equal to M2 plus M3. Then the value obtained was M2 equal to 78.8 kg per hour.
The concentrated solution at 86.3 kg per hour with 41% of potassium chloride and 59% of water entered the crystallizer. This unit produced 14.6 kg per hour of potassium chloride crystal. The remaining solution is filtered by separating it into a recycled stream with a flow rate of 68.1 kg per hour, consisting of 29% of potassium chloride and 71% of water. And the potassium chloride solution, which is M5, was directed to the storage tank with unknown flow rate. The potassium chloride solution, M5 flow rate, was calculated by calculating the overall material balance, OMB, of the crystallizer by using M3 equal to M4 plus M5. And the value calculated is M5 equal to 71.7 kg per hour.
So we move on to energy balance problem, which is considered an isolated mixing temp of potassium chloride crystallization process where the fresh feed solution is combined with a recycled stream. The fresh feed has a mass flow rate of 96 kg per hour and inlet temperature of 25 degrees Celsius and a specific enthalpy of 105 kJ per kilogram. So the recycled stream has a mass flow rate of 68.1 kg per hour, a temperature of 35 degrees Celsius and a specific enthalpy of 115 kJ per kilogram. So the combined streams exit the mixture with a flow rate of 164.1 kg per hour. Using the provided data, perform an energy balance to determine the specific enthalpy, which is H, and the temperature of T. So of the mixture at the outlet of the insulated mixing tank. So we move on to the process diagram.
So for the energy balance questions, the heat and the work interaction as well as the enthalpy of the entering and departing streams were taken into account while analyzing the energy balance at the mixer. So the formula that we use is Q plus W plus the multiple of a M in with the H in plus the multiples of a M out with the H out equal to M2 U2 minus with the M1 U1 is the equation that is applied. Since there is no information provided, eliminate the W and M1 U1s and eliminate the Q since it states that the missing tank was insulated. Substitute and determine the value of U2. Then the U2 was obtained, which is 109.15. After that, the first rules of thermodynamics to find the outlet temperature. The equation that we use is mCv dt per dt equal to mCp T out minus T reference, where the T reference is at 25 Celsius and the Cv and the Cp is eliminated because it is same since it is in a liquid phase. The temperature differential equation then changes with time. We integrate as stated in the slide. This represents the energy balance equation. The outlet temperature can then be found by substituting and converting with the provided values. This energy balance calculation allowed for the determinations of the mixture, which is 35 Celsius outlet temperature in the insulated mixing tank.
So the energy balance ensures the combined enthalpies of the input streams determine the enthalpy and the temperature of the output stream, maintaining the law of conservation of energy within the insulated system. So this principle is critical in designing and operating chemical processes, as it helps in understanding and predicting the behavior of system under various operating conditions. So effective energy management through energy balance calculation can lead to optimized process performance, enhance efficiency, reduce operational costs.
So, in conclusion, this study focused on conducting material balance analysis for the crystallization process aimed at separating potassium chloride from a feed solution using an evaporator and crystallizer. Mass and energy balance were crucial to ensure consistent crystal quality and productions. By controlling parameters like temperature and concentration, crystal growth rates were regulated to meet its specific size, purity, and morphology requirements. Through mass balance principle, the mass flow rates of stream were determined to be M2 equal to 78.8 kg per hour for the evaporator and M5 equal to 71.7 kg per hour for the crystallizer and filter units. Outlet stream composition from the mixer were XK1 equal to 0.213 and XW1 equal to 0.781. Energy balance analysis shows a specific enthalpy U2 of the mixed stream after the mixer as 109.15 kg per kg and a temperature of T2 of 35 Celsius. These findings indicate that the energy input and output for the mixing process are balanced and ensuring that the system operates efficiently.
So as we move on to recommendation part, in this crystallization process, we can improve some of the process efficiency by effective management of potassium chloride, and water inventories is essential for process stability. So this includes self-regulation, adjustment of process design, modifications to maintain optimal concentration and reaction rates. Moreover, implement a real-time monitoring system for key parameters like concentration, flow rates, and temperature can integrate advanced control algorithm to adjust cycle flow rates and other variables based on real-time data. So, Other than that, we can conduct regular maintenance and calibration of sensors and control equipment by performing process simulation and sensitivity analysis to identify instability points and improve control strategies. And lastly, we can actually train the workers in advanced control methods and crystallization details to use strategies to reduce waste and save energy, like recycling materials and finding alternative energy resources.